All right. Now let's talk about the good design. What is a good design, and how can we say that we have created a good design for our software system? So, a good design manages essential complexities inherent in the problem. Uh, Good design focuses on the problem itself and not the noise introduced by the solution. For example, a banking system must handle accounts, transactions, and security, and these are what we call essential complexity. But if we overcomplicate the system by adding unnecessary features like obscure data formats, so this is what we call accidental complexity, and we need to avoid accidental complexity in our design. Good design avoids adding accidental complexities that arise from the solution itself. So, in good design, we have the property which do not let the design create problems that were not in the original problem. For example, writing a custom encryption instead of using proven libraries adds accidental complexity and a risk. Design should be maintainable. The system can evolve without massive effort. For example, adding new payment method to Amazon's checkout system should be simple and localized, and design should be understandable. Other developers should grasp it quickly. For example, a clear naming convention and a modular structure in Spotify's playlist system make it easy for new engineers to contribute. And design should be local in effect. Changes in one part should not ripple unpredictably through the system. For example, updating the UI color theme in web app should not break the backend logic. And design should be modular. Break the system into independent components with clear responsibilities. For example, Netflix separates user profiles, recommendation engine, and streaming services into different modules. The goal is to achieve low coupling and high cohesion. So modules are self-contained and interact minimally. If we take an example of Uber, so where driver matching logic is separate from payment processing, and which make the system robust and scalable. So a great design controls the real complexity and keeps the system simple, easy to change, and safe to evolve, turning chaos into a masterpiece. Now that we already talked about the good design, let's talk about some of the design principles which you must apply while creating software design for your systems. So let me give you a real world analogy first, and then I will talk about the solid design principles. For example, you want to start your career as a cricketer. So you need to know all the principles, like if you overstep while bowling, so you have to re-bowl that ball, and it would be considered as no ball, and a free hit would be given to the batter. Similarly, if you hit the ball that goes outside the boundary by air, so it would be considered as a six, and you will be given 6 runs, right? If you catch the ball inside the boundary, so the batter will get out and he has to bat no more, right? So these are some of the principles which you need to have, which you need to know. Only then you can play a cricket match with your friends, or you can start a career in a cricket game. So solid design principles works the same in software system. If we want to design softwares, so we have to apply some of the principles, and only then our systems would be flexible, understandable, and maintainable. In today's world, if you are using WhatsApp, YouTube, or any other app like Spotify, Netflix, so all these apps are well planned, and they are made according to these solid design principles. That is why these systems are maintainable, scalable, and understandable. So solid principles make software design flexible, understandable, and maintainable. For example, a ride-sharing app like Uber needs to evolve constantly. So adding new services or payment options without breaking the existing code, we need every now and then. So solid principles guide that evolution safely. And these solid design principles was proposed by the Robert Merton, and which is also called Uncle Bob. And the acronym was later popularized by Michael Feathers. It's now a gold standard and object-oriented design. And The 5 principles, these are the single responsibility principle, where each class or module should have one reason to change, and open close principle, where software should be open for extension and closed for modification, and Liskov substitution principle, where a subtype should replace their base types without breaking the system, and then interface segregation principle, prepare many small specific interfaces over one large general one, and then dependency inversion principle, high level modules should not depend on low level modules, but both on abstraction. And then we would talk about how the solid design principle helps a developer to write code that is maintainable, scalable, and flexible, and ready for change without chaos. So these principles are very, very important, and we will talk about each of them with extensive examples, so that you can incorporate these principles while creating software design system. And the solid is the armor for your software. It keeps your code adaptable, robust, and elegant, ready to survive the storms of change. So in upcoming lectures, we will talk about the single responsibility, and then open close, and then Liskov, and we will talk about each of them with examples in Java. So the term solid, the S stands for the single responsibility principle, and the O stands for the open close principle, and the L stands for the Liskov substitution principle. Similarly, the I stands for the interface segregation principle, and the D stands for the dependency inversion principles. So that's what makes the solid design principle. Why it is called solid? So each letter in this word has different meaning. Alright, now let's talk about the first design principle of solid design principles, and that is SRP, or single responsibility principles. Because in the word solid, the first letter is S, and S stands for single responsibility principle. And that principle tells us a class should have only one reason to change. And this principle is all about cohesion, keeping the elements of a modules functionally related. And why it matters? A class should have only single responsibility. The more responsibilities mean the more reasons to change. So more changes will bring higher chance of bugs, and a class that does too much becomes fragile and hard to maintain. So what a class does, the more a class does, the more likely it will change. In real world, if we take an example of banking application, so the transaction processor class handles the transaction, and the notification sender handles the alerts, and each class has a single and clear responsibility. So if we combine both the responsibilities in one another class, so then it would violate this principle, and a class should not violate this principle. A class should have only one reason to change, and there should be only single responsibility in a class. Similarly, if we take an example of e-commerce store, where a class for the order calculator calculates the total, and invoice generator class generates invoices separately. So again, if we mix the responsibilities of these classes with one another, so it would violate this principle, and this principle should not be violated. The more a class changes, the more bugs we will introduce. SRP seems very simple, but mastering it is very hard. Keep each class focused and let it do one thing and do it well. So limited changes will cause limited bugs and a cleaner design. Now let me give you an analogy of a single responsibility principle, and real world we can have an analogy for the single responsibility principle. So let me show you a tool. Here you can see a bad class and good classes. Though in real world this tool is considered the best tool, but in software engineering, when we design, when we create classes, so the classes should have only one responsibility, and on the right hand side you can see that each of the tool is used for a specific job, but here this tool can be used for different type of jobs. So this is considered the bad class, while these are the classes which obeys, which do not violate the SRP, the single responsibility principle. So our classes should obey the single responsibility principles. Okay, now let's go one step deeper in solid design principles. So finding and separating conjoined responsibilities is much of what software design is really about. Software design is largely about discovering responsibilities and keeping them separate. For example, in a hospital management system, handling patient records should be separate from billing. Mixing them would make future changes risky and introduce bugs. SRP is the most fundamental principle, and the rest of the principles are related to SRP in one way or another. So this is the most fundamental, and single responsibility principle is the core of all good design. So all other principles like open close principle, Liskov, substitution principle, or interface segregation, dependency, inversion, support SRP in some way. So they all aim to keep modules focused, maintainable, and robust. And here you can see that you can see two types of wires over here, and these are tangled wires, and it's quite hard to manage. And on the right hand side you can see clean wires which are easy to maintain. So master SRP first, and the rest of the solid principles are easy to understand, and a class focused on a single responsibility is the first step to a clean and maintainable software system. Okay, now let's understand the single responsibility principle through an extensive example. So here you can see I have a class with the name file processor. In this class I have a function which is used for opening the file, and inside that function I have a try catch block as well, which is used for catching the exception if for some reason the file is not opening. So I want to know what is the reason why the file didn't open. So after catching the exception, the error message would be shown to the user that due to this error the file is not opened. And then after that we are going to open the log file, and we would write the exact type of error that this error was happened at this particular time. So and then we will close the log file. So what do you think, is this a good class or bad class? Is this class violating the single responsibility principle or not? So give me answer. Just take a pause and think over it, and let me know if this class is okay or not. So this class is not okay, because here we have different or multiple responsibilities of this class. Like this class is not only used for opening the file, but it is also used for catching the exception and then printing the error message, and then also opening the log file and then noting down that error in the log file and then closing the log file. So this class is doing too much. So we can split all the responsibilities into separate classes. So here you can see on the right hand side we have again the same class file processor, but this time instead of printing the error message and opening the log file, this class is only opening the log file, and if it encounters any sort of exception, so it throws that exception to another class, error handler class, and this error handler class will print the error message, and then again it will not open the logger file. It would just call the logger method to note down the kind of error in the logger file. So we have a different class for the logger, and here the logger class will receive the kind of error, and it will open the logger file and will write down the type of error, and then will close the log file. So instead of having all the responsibilities in a single class, now we have three different classes, and in each class we have different responsibility. So that's how you can split a God class or a large class into smaller classes based on the responsibilities, and only then your system would be maintainable, secure, and easy to update in the future. So there was just a small demonstration of how single responsibility works. and this is the most fundamental principle, and we need to know. So I want you to have a good practice of identifying responsibilities and splitting down larger classes into smaller classes based on the responsibilities, so that there is more cohesion and also low coupling between the classes. All right, after discussing the single responsibility principle, now let's talk about the open closed principle and what it is. Since in the word solid, after S we have the O, so the O stands for open closed principle, and sometimes it is called OCL, and which tells us that software entities like classes, functions, modules should be open for extension but closed for modification. What it means that open for extension, you can add new features or new behaviors and software system, and closed for modification, what it means is you don't have to change the existing working code. If some features are already working, so you cannot touch that code. Yes, you can extend, you can add new code, but you cannot change the existing code. Changing existing classes to add new features, you risk breaking the old code. For example, you want to change the existing code for a class, so your existing functionality are at risk, and bugs sneak in. You want to change the existing class, and you see a lot of bugs in your code, and then you have to find each of them, and then the existing functionality breaks, and it's hard to maintain, right? So instead, write code in a way that allows adding new behavior without editing existing tested code. So that is what we need to follow and our design. And this is what we call open closed principle, that a software system should be developed in a way that new features are easy to add without changing the existing code of the system. Alright, now let's understand the open closed principle through real world analogy. Let's say this is person X, and he wants to build a house. So after building a house, he can add new rooms or new dining hall to his house, and that is allowed by the OCP, open closed principle. And closed for modification, what it means is that you cannot tear down all the walls of your house, and you cannot change the structure of the existing room, right? So that is what we call closed for modification, because if you tear down all the walls and if you want to change the structure of the room, so then that is the violation of OCP, and we don't have to violate the OCP. Yes, we can add new rooms, or we can add new floors on top of the roof, but we cannot modify the existing rooms, like the changing the structure or anything like that. So that is what we call OCP, open for extension and closed for modification. You cannot modify the existing structure of the system. Yes, you can extend it, you can add new classes, you can add new functions. Instead of changing the existing function or classes, open closed principle tells you to add new ones. Alright, now let's understand the open closed principle through Java code example. So here you can see I have a class post. In this class post, I have a method called create post. And this method I have passed two parameters, one of instance of database, and the other one is just string type of message. But before storing this message or creating this post, I want to check that what type of message or post this is. So if the post message starts with hash, so this is a tag message, and it should be stored in this particular method. But if the message does not start with the hash, so then it is a post message, and it should be stored with this method, right? So these are two types of messages which can be stored for, which can be posted by this create post method. But let's say in future you want to add another type of message, like the mention message, where one person mentions other person. So then we have to make changes in this existing class. And when you make changes in the existing class, so that is where we violating the open close principle, and we shouldn't be doing this. So this is not a good approach. This class is not open for extension, yet you have to modify this existing class, and which is not recommended, and which is the violation of OCP, open close principle. Now let's understand the solution, that how can we solve this problem, and how can we follow the OCP or obey the OCP. And if, for example, in future we want to add more type of messages, so we can easily extend the class without modifying the existing class. So how can we make this to obey OCP? So let's move to the next slide, and where we would like to solve this problem using or obeying OCP principle. Okay, now let's solve that problem. So here you can see I have a class post, and this class post I have a method create post, but I didn't add all type of post to be added. I have added just a single or simple method of add of class DB, right? So I am writing this method in this class, and if I want to store a specific type of message, so I would like to extend this class. For example, I want to store tag message, I want to store post message, I want to store mention message. So what I can do now, it's quite simple. Instead of changing this existing class, I can extend this class. From extending, I mean I can inherit this class in my new class, and then in that new class I can add new feature instead of changing the existing class. So by doing this, we can actually follow the open close principle. So here you can see I've extended the post class, and I added the tag post, where I would like to store all the posts that have tags. So here you can see I have provided the definition. I have overridden this method create post, and this method is storing the tag post in a different file, right? And in future, if you want to add the mention post, so again you can extend the same class, and you can provide or you can override this method and that mention class as well. And so by doing this, we can actually follow the OCP, open close principle. And this is very, very important, that a class should be closed for modification and open for extension. So now this class is closed for modification, you cannot modify, but you can extend it. And in fact, we have extended, so we can now have scalability, or we can easily maintain the system in future. Alright, now let's talk about the Liskov substitution principle, which is the third design principle in solid design principles, and which is also sometimes called LSP, and it was defined by Barbara Liskov in 1987, and which ensures that subtype can replace their base types without breaking the program. So what it means, if S is a subtype of T, and then objects of type T can be safely replaced with objects of type S, and the program continues to work as expected. And this prevents violating the parents class's expectation. So why it matters? Because it ensures the correct behavior with inheritance, and promotes polymorphism, reusability, and robust design, and also prevents bugs caused by inappropriate subclassing. And if we take an example from a real world, let's say we have a system in which we have a base class user, and that base class can have subtypes like free user, premium user, and anywhere the system expects a user, it can handle free user or premium user seamlessly. Similarly, if we have a system in which we have payment system, so base class payment method can have subtypes like credit card, PayPal, Stripe, and code using method works regardless of the specific subtype. So LSP is the promise of safe inheritance, and subtypes honor the rules of their parents, keeping your code flexible, reusable, and bug resistant. Alright, now let's talk about an example in which the Liskov substitution principle is violated. And here you can see we have a super type bird, and the bird can eat, can fly, right? So these are some of the properties of bird. Now we have some subtypes for this super type, like sparrow. The sparrow has all the properties, like sparrow can eat, sparrow can sound, sparrow can fly. But if we make a subtype penguin, so penguin can eat, penguin can sound, but penguin cannot fly, and which is the property of its parent. So now this is what we call the violation of Liskov substitution principle. So whenever you are making your software system, so you need to be very careful with your subtypes and supertypes. These subtype should not violate the properties which are decided, which are defined in the super type. So the subtype should respect all the properties which are defined in the super type. So in this case the penguin cannot fly, so this is the violation of LSP. Alright, now let's talk about the fourth design principle, and that is interface segregation principle, and which is also called ISP. And this principle tells us that no client should be forced to depend on methods it does not use. For example, you have an interface, and in that interface you have defined a lot of methods, and the client is interested in only one method, and the rest of the methods are useless for the client. In other words, the client is not using those other methods. So that is what we call the violation of interface segregation principle, because the client is interested in only one method in that interface, and you have a lot of unnecessary methods as well, and we need to create separate interfaces for all those methods which can be used by the client separately. So instead of having large fat interfaces, break them into smaller, more specific ones, and this promotes high cohesion and low coupling, and which also helps avoids situation where implementing classes have to provide empty or irrelevant methods bodies. So for example, if a client is interested in only one method, but he is implementing a particular interface in which all other methods are also declared, so the client has to provide empty bodies for those other methods as well, which is not really required. So we need to remove this extra work, and we need to create only interface of methods which can be used by the client. Leads to flexible, maintainable and scalable code. So if we apply or use or follow this principle, so we are going to get flexible, maintainable and scalable code. Now let's discuss an example which will further enhance your understanding of interface segregation principle. And whenever you're designing systems, so you can easily spot that if you are violating ISP interface segregation principle or not, or you have to respect ISP. So here I have an interface called worker. In this interface I have two methods, work and eat. So this interface can be implemented by human, because human class can provide the definition for both work and eat, because human can work and human can eat. So for example, if I want to implement the same interface via robot, so now this is the violation of single interface segregation principle, because the robot cannot eat. The robot will override the work but cannot override the eat method. So that's why this is the violation of interface segregation principle. On the other hand, if I create two interfaces, the one is called workable and the other one is eatable, right? So now if I want to implement, so the human can implement this interface eat, and the human can also implement this workable interface as well. So now this human class is implementing both of the interfaces, and the robot class cannot eat, so the robot class is only used for implementing the workable interface. So now this is the demonstration of how can we follow the interface segregation rule. Now the interfaces are segregated into a different smaller and focused interfaces, and that is what we need to incorporate in our design system. Only then our system or softwares will be maintainable and flexible and more secure. Okay, now let's talk about the final design principle, and word solid, the last letter is D, and D stands for dependency inversion principle, and the short form of dependency inversion principle is DIP, and which tells us that high level modules should not depend on low level modules, and both should depend on abstractions. Abstractions could be interfaces or abstract classes. For example, you have an e-commerce store, right, where you have a high level module like order processor, and that high level module is dependent on low level modules, for example payment method. And if the payment method is changed from credit card to Stripe or PayPal, so then you have to change the high level module order processor as well, and that is the violation of dependency inversion principle. So we need to keep in mind that we have to follow dependency inversion principle. Only then we can make our system flexible and easy to change and scalable, right? So abstraction should not depend on details, and details like concrete implementation should depend on abstractions. So without incorporating dependency inversion principle, the high level logic becomes tightly coupled to low level details. Just a moment ago I gave you an example of how the order processor is dependent on the payment method. So then the system can become very rigid and hard to change and fragile, and a small change breaks many things, and the system becomes difficult to test. So we need to incorporate dependency inversion principle, which if you incorporate, so you can replace low level components without touching high level modules. For example, the order processor class is dependent on the abstraction payment method, and that payment method could be implemented by any of the payment method class like PayPal, Stripe, credit card, or any other. So if you change the concrete implementation for that interface, and the interface is the payment method, and that payment method interface can be implemented by credit card, PayPal, Stripe, or any other payment method class. So you don't have to change the order processor class, because the order processor class is dependent on abstraction, not the concrete implementation. So we need to incorporate this principle as well if we want to make our system more scalable and more maintainable. Now let's take an example of how dependency inversion principle can be violated, and then how can we solve that problem by following dependency inversion principle in our code. So let me show you a Java code, and here I have two classes. The one is MySQL database and the other one is user services, and this user services class I'm using the instance of MySQL database directly over here. So now this is the high level module user service, right? And this user service class is directly dependent on the MySQL database. And tomorrow if this MySQL database is changed, for example I want to use PostgreSQL or Oracle database, so then I need to change this high level module as well, and this is the violation of dependency inversion principle. because the high level module is strongly dependent on the low level module, and if the low level module is changed, so then we have to make changes to the high level module as well, and this is something which we want to avoid in our software system. So we need to follow the dependency inversion principle in order to solve this problem. So here you can see the low level module and the high level module, and the high level module is strongly dependent on the low level module, and this is something which is wrong, and we need to avoid this type of classing and classes. We don't have to write code in such a way. In fact, we have to make abstraction, and this high level module should depend on that abstraction, not directly on this low level module. So now let's take an example of how can we solve this problem. So here you can see I have added an abstraction interface database. Now this interface can be implemented by any database, whether it is SQL, whether it is Postgres or Oracle or any other database. This interface can be implemented by any type of database. And for example, I have implemented this interface via MySQL database class, right? So now if I want to use this database in my user class, so here you can see again that high level module. I have a database instance, database DB, right? But this instance is of type this interface. So this interface can be implemented by any class. So now this high level module is not dependent on the concrete implementation. Rather than depending on the concrete implementation, this class is now dependent on the abstraction, and the abstraction here you can see this interface. So this interface can be implemented by other classes as well. Here if I add another implementation for the same interface, so here you can see Postgres SQL database can also implement this interface, right? So I can implement this interface by any type of database, right? So if the low level module changes, so it won't affect the high level module. In this case, you can see the interface is implemented by both of the classes. So we can do this, right? So we can do the same with payment method as well. So instead of the order processor class, depending on the concrete implementation of the payment method, we should make depend then that class on the abstraction in a very similar way to this, right? So the good thing about dependency inversion principle is that if you follow the DIP or dependency inversion principle, so it would provide you with the natural progression of the Liskov substitution principle and the open close principle and even the single responsibility principle. So you will get the automatic implementation of or the automatic following of those principles. So dependency inversion, dependency injection removes hard dependencies by shifting from composition tight coupling to association loose coupling. So instead of making a system of another part, what we do that we separate that part and we make a separate class for that part, and then we make association from original part to that separated part. So that is what we call dependency injection, and by doing this we can actually make the software flexible and testable and maintainable, where high level modules do not need to know the details of low level modules, and that is what we are trying to do with DIP, dependency inversion principle. And I've already given you an example about payment processor where it depends on payment gateway interface. So dependency inversion principle is the secret behind flexible and loosely coupled system. So your code depend on abstraction, not implementation, and which makes the system easy to change and risk free.
Thank you so much for watching this. Before you go, please don't forget to subscribe to my YouTube channel and turn on the notification bell so you never miss any of my upcoming videos. I regularly share valuable lessons, practical tips, and step-by-step tutorials to help you improve and grow. And if you are serious about mastering software design and architecture and want a complete structured learning experience, so I have created a full course that includes detailed lessons, assignments, quizzes, and downloadable workbooks to help you practice and apply what you learn. So if that sounds helpful, just check the link in the description below and enroll in the course today. I would love to see you inside and support you on your learning journey.